Hello, hello, hello. Welcome to the stream, Gene. Welcome to the stream, DigiRen. Good to see y'all. Got Monochroma here tonight.
Hello.
We got a JEOL 6400. We've got a Thermo Ultra Dry EDS detector and a Norian System 7 back there. Got a Norian computer. And over there, on a sample prep bench you all haven't quite seen yet, we have all of the wipes that we use to clean out the chamber of the Merlin. So what happened to Merlin?
Merlin died.
I mean, it was running when it left. Something happened to Merlin. There was metal. There was like a lot of metal in the chamber. I don't really know why there was metal in the chamber, but we're gonna find out. we're going to find out what it is, and that's going to help us figure out why.
Yeah.
So, yeah, it's just concerning, right? Like, we have a working theory. Our working theory is that, well, first off, the turbo pump that's on Merlin right now is not the turbo pump it shipped with. It's a much nicer turbo pump than the one that it shipped with.
Yeah.
It was also in a fab environment, or adjacent to a fab environment, so uptime, very important probably, right? So we think they had the old turbo. We think the old turbo might have crashed, had a little bit of an accident. And they're like, okay, put a new turbo on it and get it going. And so we think it's turbo pump debris.
Yeah.
And we think that that's why there's so many small shards, because the pump is spinning very quickly. We just couldn't really identify anything else that could generate this type of debris. So getting some imaging of it, getting some elemental analysis of it will give us a lot of good information to figure that out with. So let's see here. We're going to start actually though with the open beam interface here. So got a open beam interface here. This little cable is for like flipping a relay inside of the SEM. And we are going to be installing the software on the computer and putting the open beam interface on the SEM. And then we're going to use this to do our imaging of our metal. So yeah, feel free to ask any questions as we do this. We're going to start with software, you think, or do you want to start with hardware?
Software probably?
Yeah, let's start with software. That sounds good. Okay, so I'm going to get the good old screen share going here. Let's see here. Let's do this. Let's do I have a screen share? I have a screen share kind of set up. Well, it's not, that's not really set up. Let's do this. Let's duplicate that. We're going to add a source. We're going to add a Mac OS screen capture. Add existing Mac OS screen capture. And then we're going to make us small. And we're going to make the screen capture work. Ooh. We did things. Okay. So what do we need to do for open beam interface? First, we need a terminal. And we also want the installation instructions, which I got right here. So we're going to go to where we want to do this, which is going to be, I'm going to put, in this case, I'm going to put it in the documents folder. And once we're in the folder we want to do the installation in, and I'm just going to check OBS, make sure it's streaming what we want it to be. Oh, that was our terminal. We are going to do our first command here, which is our git clone command. That is basically going to download open beam interface onto this computer. So prerequisites for this that we haven't shown yet is you need Python installed. Today we're using, we're on 3.13, right? I think is what we left on this computer.
I think so.
Yeah, I think we're on 3.13, and then you also need to get PDM installed. And to do PDM, you need to do Homebrew. And Homebrew kind of takes a second, so did that before because we didn't want to wait for that initial Homebrew install, which takes a little bit. So. So we did.
And PDM actually also does the Python environment.
Yeah.
Because because macOS comes with an older version of Python, and then PDM sets up the correct whatever version of Python that we need.
Yeah. So let's do. So once we have the git clone done, if we do ls, we've got open beam interface folder. So let's go into open beam interface. Once we're in here, we've got a couple of folders. The one that we're going to go to for now is going to be software. So let's do cd software. Once we're in software, we're going to do PDM install. And that's going to pretty much take care of everything we need for OpenBeam interface here. You don't have to, but you can use an existing Glasgow installation. But right now, we are just letting the OpenBeam interface take care of our Glasgow. So now that we have that installed, we're going to do PDM run launch. And launch is something that is set up for OpenBeam interface that will launch this window right here. And this lets us run the OpenBeam interface server and run the OpenBeam interface GUI. Okay, and we do have an error right now. So we have no such file or directory microscope.toml. So what's going on there is every microscope can be a little bit different. So we are set up to have a configuration file to define how your microscope works. So we need our example toml file, which is under, let's see here. There we go. It's under configs. And we're going to be using the JEOL 840, 63, 6400 toml. So we're going to copy that into the top level of our software folder. And we're going to rename that to be microscope toml. And so I'll just go ahead and show you what's in our toml here. We don't want to do that. We want to just want to do text edit for now. So this is pretty simple. So we tell it what pin we want to use for our external scan enable. In this case, we're using pin A0 on Glasgow, although for a reason we'll get to a little bit later tonight, we're not actually using that. And then we have our transforms and our rotates. So our transforms and our rotate basically flips the signals around because some microscopes, the top left corner of the screen is positive voltage and the top is a positive voltage in X and Y. And some microscopes it's a negative voltage in X and Y. So that's why we have the rotates and the flips. And then we've also got a delay. So this is how long it waits to start scanning after the relay flips. So this is settings we found to work really well for this particular microscope. So we're going to go with that. So now we've got our toml. We can go ahead and run that again. And this time, OK, we've got our OpenBeam interface GUI. That's shown up. That's great. However, we are getting a Glasgow device not found error. And that is entirely expected because I'm holding it, and it's not plugged in via USB yet. So we go ahead and take our USB-C cable here and plug that into Glasgow here. We got some very pretty lights now. And we can go ahead and run the server again. And now it's building the bit stream. So that's the bit stream it's going to configure the FPGA with. It checks if the bit stream is cached. The bit stream is not cached because this is our first time we've run Glasgow. So it wrote the bit stream. And then once we get the, a really good thing to look for is if the voltage is set. So once the voltage is set on like the A and B ports here, everything's been done basically. And we've also got our server is running and our socket is ready to go. So from there, we can start scanning. Now there's not actually, we're not scanning because they're not plugged into the microscope yet. And that's what we're going to do next. So that is how you install OpenBeam interface software. So let's go back to, oh, we're a little bit cut off. I see. Interesting. I did not realize that. This is why we should be pre-flighting our OBS setup just a little bit more. Yep, I can see why that has happened. So cut off a little bit of what I was doing, but I think I got most of it. This must be because it's a 4K screen. It's a 1080p stream. OK, so I'll just show you all just a little bit of what you might have missed. So there's our OpenBeam interface GUI. Here's our dialogues, and that's not what we wanted. So what I had to do is I had to go into our configs here. We have a couple of example configs. I right-clicked, copied our JEOL config. I brought that back up to the top level. I pasted it up at our top level, and then I renamed it to be microscope.toml because that's what actually gets looked for when the software runs. So that once our config was loaded in, I was able to successfully run the OBS server and the OBI server and OBI GUI. So we're going to go ahead and close both of those for now. And then all of the installation instructions are on the Open Beam Interface Documents page. So all we did was we did the git clone. We went into the software folder, and then we ran pdm install, and that took care of us. And after we ran pdm install, we ran, let me just close this so I can show you that again. We did our pdm run launch. And that is what brought up this GUI that we can run the server and GUI from. And you can also individually, if you want to bring up like 2 terminal windows, you can do pdm run server, pdm run GUI like separately. And that also works. This is just kind of a convenient tool. So anybody have any questions? So okay, so let's see here. What detector are we using for analysis? Just BSD? We do have a EDX that's a little bit out of view. It's on the kind of back right corner, but I think you will be seeing that shortly. So do you want to grab the R6 and we'll start working on plugging in the cables behind the microscope for this? Sure. So now that we've got the software running, we're going to go ahead and go behind the microscope and start plugging in some cables to the external scan interface. And then we're going to come back here and plug cables back into OBI and start going. Did the camera make choices? There we go. Cool. That should work. Yep, we're live with it.
Come on. The tripod is not cooperating. Thank you.
So first thing we're going to do is we're going to turn off our high voltage so that we're not working around the detector and electron source high voltage while we're back there. So high voltage is off, so we'll go ahead and plug some cables in. So actually, I'm going to show the little board I built to do this. You want to bring the camera over here? So this is a JEOL interface board that I constructed a while ago for this microscope. It's pretty simple. So this is the JA7 connector, which many, many JEOLs use. And newer JEOLs have a D subversion of this, basically. So this has got some scan pins on it. And it's also got some external enable and external blinking pins on it. So we've got 2 B and C. So these takes the X and Y signal from OBI and puts it into the JA7 connector. And then this M8 connector flips this relay. And the point of this relay is that it shorts together 2 pins on this connector. And when those particular 2 pins are shorted, that tells the microscope to flip over to external scan. So in this particular installation, we're going to be letting the microscope flip the external scan using its internal relays. We haven't tapped into the scan signal somewhere so that we can put our own relay in and flip them ourselves. Sometimes you want to just take more control of what's going on in the microscope than the external scan interface would allow you to, and that's where you want to kind of put your own relay board in somewhere. But on this particular microscope, the external scan interface works quite well, so we're just going to be using the internal relays today. We're not going to quite be using this particular board though, so we also want to be running our X-ray analysis. And the X-ray analysis also sometimes uses the scan port. So instead, we're going to be using a different microscope external or JEOL external scan breakout that lets us also plug the X-ray in simultaneously. So if you want to show the X-ray detector, that's the Thermo Ultra Dry, what is this one? 132 EV SSD detector, SDD, silicon drift detector. So that's what we're doing our X-ray analysis with. We got the NORAN System 7 down here. Currently, if you want to come down here, This is our cable from, this is our cable from System 7. It is plugged into JA2. I misspoke earlier, I said JA7. JA2 is this microscope's external scan port. So with this plugged in, we don't really have any room for open beam interface to be added in here. So we're going to go ahead and we're going to remove JA2, which is currently coming from NORAN System 7. I didn't quite release on the bottom there. There we go. So NORAN System 7 is now unplugged. And I've got this little box here. So this box is very similar to what was built here, except it also has another one of the same type of connector that JA2 is, and it has BNCs. So what we can do with this is we can take the cable that comes from our EDS controller and we can plug it into here and connect it. And then once we put our open beam interface inputs in here, we'll be able to either use open beam interface or the EDS without having to come back here and unplug cables. So this is the power for this particular box, because this box needs 5 volts for its relays. And this BNC cable here on the enable pin goes to a little manual switch on the front of the microscope that lets us flip back and forth. And then these are X and Y inputs. So I did run the cables earlier for this. I've got the BNCs we're using for X and Y that are going to connect to open beam interface in the front. So we're going to take these and we're going to go, X is going to go here and Y is going to go here. So that is our scan signals routed. And so now we're going to plug that back into JA2 and make sure that gets latched in, and cool. So that's our scanning done. So those are our X and Y inputs. The other thing we need is we got to get video signal back out of the microscope. So for that, I've got our BNC that we're using as the detector down here. And on this particular microscope, we are using NA7 down here is our primary image output. And so there is currently, and we can zoom in on that, there is a T installed on NA7 here. And I don't need to take away the image signal from the microscope. I just need to tee off of it. So we don't need any relays or anything. All we need to do is plug our detector cable for open beam interface into a T on the microscope. So now we've got our detector signal teed off of NA7, and that's basically everything that we have to do behind the microscope to install open beam interface. I also put a power cable in for open beam interface up here. This power cable is ran off of the accessory power supplies. So that gets us our ground, our 5 volts, and our plus and minus 15 volts. And by utilizing the power supplies that already exist within the microscope, we kind of adhere to the microscope's grounding architecture and power distribution architecture and minimize the potential for ground loops or other issues of the sort. So let's go around back and we'll finish plugging cables into OBI, and then we can go ahead and get an image. Have a lovely evening, DG Ren. It was good to see you. So we've got OBI right here. And then if you want to zoom in on it with the lens, so we plugged in 4 cables in the back. We did power, detector, and our X and Y. So let's go ahead and plug power in. I don't always necessarily recommend just hot swapping power, but it has been extensively tested, so we can just plug power in. There is a sequencing on the power supplies, so they only turn on in the correct order. So we got power plugged in, and now we're going to get our X plugged into our X BNC there, and we're going to get Y, and we're going to plug Y into that one. And our detector, we're going to plug into that one. So we're done messing around behind the microscope. So we can go ahead and bring up our high voltage now. So we're at 15 kV, filament current knob is 0. So we're going to go ahead and turn high voltage on. And now we
I heard it.
What? So with high voltage on, we can go ahead and we'll go back to our screen share real quick. We're going to run our server. We're going to run our GUI. And I'm going to switch the OBS input around a little bit. We're going to change that to an application. And we're just going to capture the Open Beam Interface GUI here. And we'll go ahead, we'll throw another camera in here for y'all. And let's do our 6D, there we go. And we can also throw the webcam in.
It needs to be plugged in first.
Oh, do you want to do that?
Do we have cables?
I think so. Yeah, we got cables. There we go. It's right there. That's a monochroma is very good at realizing when when I've not properly plugged a cable in. I'm very appreciative of that. Hey, look, another camera. That's a fun view. I like this. Okay. So let's go ahead and we're going to start scanning now. So we'll start our live scan. We'll do 512 dwell time 2. So let's turn up our contrast, see if we get some detector snow.
I think this one crashed.
Camera crashed.
Something.
Yeah, it is a little bit frozen, isn't it? How's it looking now?
No change.
Ah, this is an OBS 32.1 bug actually. You have to, okay, yep, we have to unplug and replug the capture device because what happens is I basically go like around in a circle. Whatever the last camera I like turn on and off, it freezes the one right before that. But unplugging and replugging kind of restarts it. So as long as that's the one that's frozen, we can unplug and replug to fix it. So, okay, there we go. Let's do the one little thing I have to do to make this happy.
It's easy to get rid of the no card in camera.
It's what?
It says no card in camera.
Yeah, it's not easy to get rid of that, so we'll just cover it.
Yippee.
We need different firmware on the camera to get rid of it completely. Okay, there we go. So now we're going to, so we can see our brightness control. So brightness is working great, love that. Our little internal switch is flipped to our external, so that's gonna enable the Open Beam Interface scan inputs. And we can start saturating our filament. So we're starting to get some electrons going up. That's our false peak, and we'll keep going. And there's our actual peak. So now we're just going to maximize that. And there we go. That's Open Beam Interface. And we are scanning. We got an image. So that is the basics of how you install OBI on a SCM, the likes of a 6400. So if anybody's got any questions, now's a great time to throw them in the chat. We'll do a little bit more just with the just moving around and imaging some of the OBI, and then we will move on to our sample preparation. So we've got a calibration target in here right now. This is a tin on carbon target at the moment. Do some stigmation. The image is moving around a little bit right now because this whole thing's on springs and I bumped it. We'll go 1K scan, we'll do dwell time, dwell time 2 is fine. So changing focus, okay, we got a little bit of wobble there. And now we are at this particular microscope's current noise floor. We suspect a scintillator power supply issue in this platform that is leaking 60 hertz in through the 10 kV and causing the beam to deflect. But we're doing EDS tonight, so we don't need to zoom in very far. We're zoomed in at 40,000 right now. What we're really going to be using is that really high spot size. So yeah, so that is our install. Let's go ahead and get our sample prepared. Does that sound good?
Okay.
Okay, so we can go ahead and point the camera over here.
Swap it to that tripod.
Yeah.
Yeah.
And then let's go ahead and do our lens change here. We're going to do the macro so y'all can really see what we're working on. So I'm going to take it, yeah, you can use autofocus or you cannot, up to you. It's the switch right here on the side of the barrel.
Okay.
And then it's that forward one. We'll take that off.
This one? Or
Yeah, the big ring.
big ring?
Yeah, and then we're going to go ahead and do manual. And what that's going to let us do is set a much smaller aperture. And that's going to get us a lot more depth of field. And then if you touch somewhere, that gives you the focus guide. And when the focus guide is like green, but it's not going to do very well unless you got something that's like some contrast on it.
Mm-hmm.
You see when the arrows are close, that means it's in focus. So yeah, are we looking good on exposure? I think we're doing decent. We'll go a little bit less. There we go. So let's throw some gloves on. Touch the fingers on that one. Got more than we bargained for there. So how's everyone doing tonight? Okay, so let's get a stub out. We'll get a stub in a box here.
Does this have zoom?
What? It does not have zoom.
Okay.
Fixed focal length.
All right.
And then I'll just go and put it in autofocus.
Yeah, it's easier.
Yeah. So there's our stub. So we're gonna go ahead and open up our jar here. So this is the samples we took from Merlin. Oh, assembly-rific. So happy to hear you're having fun with your assembly. So we're gonna go down to some of the lower ones that are in here, because those first ones were really what had all of our metal shavings, right? Does that sound good to you?
Mm-hmm.
Cool. Okay, so kind of, we'll lay these out sort of in order. Okay, so we got our very first one here. I know I folded that one up, and I think the first two really had some good pieces in it. Set that off to the side. We're going to be using a conductive carbon. I hope this one's conductive. I did have one set of them that was a little bit weird. I don't think that's. Oh, these are the really smooth ones. Okay, you know what? Actually, we're going to do the one I know is going to work fine, and that's going to be our conductive carbon tape. One time I ended up with a set of carbon dots that wasn't actually conductive. I know, right? And like, it's so I don't. They've spread. So we'll do like that, and then touching things that are not as clean now. So we're not touching our samples anymore. We're going to go ahead and do the little snip snip. Done our snip snip. So press that down really nicely. And we will try to get focus going.
Yeah, it's being silly.
Cool. And so we'll go ahead and peel off our double-sided tape. There we go, we got some carbon. That's a particularly rough one. Okay. Are these the conductive ones or are these not? I hope they are. Because the advantage of these ones is these are very, very smooth. We'll go with what we know is gonna work. So now we're going to go ahead and unfold our first thing we wiped the chamber out with. I don't know how clearly it's coming across on camera, but I can definitely see like a lot of little glints of metal. We'll just kind of tap this a few times so they all kind of go into that V. Okay, we got a nice set of all of our stuff that we're trying to target tonight. So I think it shows up on camera probably, that all that debris, that line right there. And before we start messing around, I'm going to just move a few pieces over manually, I think. Actually, we'll just try it. We'll see if we can just kind of gently stick it to stuff. Oh, that did a great job. Got a number of pieces of metal on there now. Let's kind of do that a few more times. We might end up with some fibers on this as well, but I think that will be just fine. Okay, so that's pretty loaded, I think. I'm going to bring it up real close. bring it up really close. Here, I'll just move it from here. So there's a bunch of stuff from the Merlin chamber. I think that looks like a pretty good sample to me. What do you think?
Yeah. Lots of whatever that is.
Lots of whatever that is. So I'm going to go ahead and put the rest of this back in the jar, kind of in the order I removed it. We'll throw this in, we'll throw that in our case for now. So that's our prepared sample. We'll fold that one back up. And let's put these back in. Okay, so that's our sample preparation. So now we're going to switch back to our other lens here, and we're going to go ahead and load lock our sample out. Does that sound good?
Yep.
And you're in autofocus. Okay, do you want to pan over to the microscope and we can do our sample exchange? Yeah, I am thinking about the fibers possibly, like the possibility of the fibers charging up and deflecting anything. I think we're going to be okay. The metal pieces are quite large. It might be in manual mode. So you do the top left corner, where it says like little M or something like that. Yeah, it's that button, and that switches between the two.
Okay.
Yeah. Cool. So let's go ahead and do our sample exchange, because this is a JEOL 6400, and they all come with a load lock, and it's amazing. So we'll go ahead and put our sample exchange rod in. We'll hit our red button. We're going to pump our load lock down, and we're going to go ahead and turn our beam off. So now we're just waiting on our load lock to pump. If you want to look at our vacuum state diagram down here, we are currently using our roughing pump to pump through V6 and through V5 to pump down our load lock. And what it was doing previously was we were pumping through V2 to back our diffusion pumps and our diffusion pump buffer tank. But because we have a buffer tank, we can close V2, open V6, open V5, pump down the load lock, and then flip back to pumping the diffusion pumps, and we can do that all just with one roughing pump. So, okay, so our load lock cycle is complete. We can roll the knob 90 degrees back, so you go from there to rolling it towards you, and then you can open the door. Do you want to see if you can point the camera down here? Let's zoom in as far as we can. And then I'm going to lower the stage down, and we're going to manual focus because it's not going to want to focus back there. There we go. Yeah, yeah. Here, do you want to come past the end of the sample rod, maybe? And then try and do some focus. Yeah, it's
The string?
Yep. So we're going to be bringing our stage down. And then we can also increase the exposure by doing that, and that just like sets the, it tries to auto expose higher. So we see all the way back in there. So we're pushing our sample exchange rod all the way back. I need to actually look at what I'm doing. Okay, I got to move the stage over a little bit. So just a little bit up, maybe, or I guess down. I guess I was going to see it. There we go. Okay, I can kind of see what I'm doing through the camera. So moving the stage over to line it up, and then we're going to thread into it. Oh, I'm going to come up actually and do the lower one of the holes. That'll be easier, I think. Oh, not rotated correctly. That explains a little bit. There we go. Yeah, doing this without looking is hard. I need more practice, apparently. And then the other thing is I had the sub Z at the wrong height. So there we go. Oh, that's a great shot of it. Okay, so we're threading in. I think I'm threading in. I might be threading in. Oh, I'm tilted too. There we go. Now we're threading in. Okay, so we've got that threaded in, so now we can pull it out. And we have retrieved our sample holder into our load lock. So we'll go ahead and close our airlock and press the button again. That's going to vent it, so I'm ready to catch it. And there we go. That's the sample we had in it. So now we're going to head back over to this bench. We'll just set it on the bench and unload it. Return our sample exchange rod. So that's the calibration sample we had in there. That's a FEI calibration sample. Do you happen to know the whereabouts of the screwdriver roll kit?
I feel like I've seen it.
I thought we brought it over here.
Oh,
but then we
here it
couldn't.
is.
It is. Oh yeah, we did bring it over here with the specific intention of using it for this purpose.
Indeed.
So we'll get our Phillips out. And loosen that. Okay, that's a bigger Phillips than I got in this kit, but I might have lined something up correctly. Did not. Okay, we'll use the pliers to do this. There we go. So that's released the inner part of that. Oh, this one doesn't, that one, it just fit in there like that. That's kind of funny. Oh, it's really in there. Okay. There's really no set screw on this one? There is a set screw. Okay, that's what I was expecting. Don't know if that was the right size or not. That's probably one too small, so let's go one size up. I think that's one size up. What's that? That's a 2, that's a 1.3, so it should probably this. That one can't go far enough. Okay, I'm gonna grab a set of Allen keys real quick. I'll be right back. Okay, we've retrieved the Allen keys, and we got the 2mm key. Now, we can free it. No, it is smaller than 2. Okay. It's the 1.5. Oh, I used the 1.3 and the 2. I didn't use the 1.5. That's probably why. Is 1.5 in here right now? There's the 0.9, there's the 2, there's the 1.3. Yes, the 1.5 is not in the kit. Okay. So will this one reach? Apparently not. see here. I think I got something else that'll work though. That should do the trick, I bet. Okay, one size up from that, maybe. There we go, that did it. Now that loosened the set screw, but we're still a little bit stuck in there.
Do we not have another sample holder available?
We kind of do, but this one's particularly well suited for EDS at this particular height. So I would like to use it, but we will switch to our backup very shortly if this does not work out. Okay, that is certainly in there. So we're just gonna leave this in our desiccant cabinet for a bit, and we're gonna switch to a different holder. Okay, the question is, which one do I want to use for this? We'll go ahead and use that one. I think we can make this one work. So what I'm going to do is we're going to run this one as tall as we can. So the height we want this to be at is the height that the top of this is at. So we're going to be a little bit low, but that'll be just fine. And we're going to use some double-sided tape here. We're going to cut just a few small pieces. And we're going to grab our sample, and we're just going to stick it on that. So we're not too terribly far off from our target height. We're maybe 5 millimeters lower than we ideally would be, but that's not too bad. And then I'm going to take a picture of that. So that we can navigate. And we'll get the sample exchanger out and put it back in the microscope. Go ahead and thread on. Threads caught a little bit earlier than they probably should have, so that's interesting, but that's just fine. Those 4-step tweezers are indeed for holding those stubs. I got a variety of those. I do like those ones. And I got a bunch of different types of tweezers for holding stubs. It is relatively common to have the turbo pump directly under the stage. That is, you have, Map Labs, you have correctly identified the potential challenges with that design though. So we're just waiting for our load lock cycle. This will wrap up in a second. The exposure set high, but yeah.
That one?
Yeah. Neutral's in the middle. Yeah, and you can click the back arrow to get out of it. Cool, so that's our pump cycle. So now I can open up our gate valve up here. So we'll roll that towards us, pull that, and now we can check out in the chamber. We're gonna push our sample rod in. Oh, I gotta bring it up one because we're doing the shorter holder. Okay, so I'm on the dovetail. So the sample rod's gone all the way back in. So what I have to do is move the stage. So you see the sample rods, if you want to look at it from the side, sample rod's connected to the stage right now. And so by moving the axis of the stage, I'm bringing the sample rod out far enough to be able to unthread it. Okay, that feels locked in, so we'll go ahead and unthread our sample rod now. So I'm real confident it's unthreaded, and I'm gonna watch it as I pull it out to make sure I'm not accidentally dragging the sample out. So if you want to try and get a shot down there, we can see the, let's go ahead and bump that up. Yeah, so you can see our sample there, and I'll go ahead and tilt the stage so you can kind of see what part's tilting. That's our sample all the way in there. Cool, so let's close our gate valve. And there we go. And we can just put the camera back on the regular tripod now.
Okay.
So we got a sample on the microscope, so we can switch back to that, and let's go ahead and get ourselves a beam. Bring the sample up to the height we're going to use. It's going to be approximately 15 millimeter working distance. High voltage on. Bring up contrast, bring up brightness. Okay, V7 cycled a little bit there, and our current meter is not on, so we got just a second to wait for some air to get out of the system. There we go. Okay, high voltage up. Let's warm our filament up. Well, I haven't fully saturated the filament yet, but we can see ours. Oh, that was not happy. What did you do? Huh, interesting. V7 cycled twice now. Why is it acting so weird? It's so V7 cycles when the pressure is not met. Again?
It's a gate valve, maybe.
Could have a leak on the load lock.
Yeah.
So if it's a load lock leak, pumping the load lock down will take care of it. I'm gonna grab a multimeter and see what's going on with that.
There's one on the bench.
So we want to check PG2 is what sets the gun interlock pressure. I don't have clippy probes right now, so I'm just going to be holding these on, so that's going to be fun. Okay. Is that just removing these probes, or what's going on? Maybe I should have just grabbed the clippy probes. If it's moving around like this, or the pressure's just going up like this, that's not good.
Does that mean hold it?
I'm gonna get better probes for this purpose, because the reading is unstable now. So I was like, was like, if I could get away with just holding the probes on, then, you know, that'd be fine. I could get the information I need, but now the question is was the probing bad, or is the gauge actually unstable? If the gauge is actually unstable, we've got to kind of figure out what's going on with that.
How are we doing on time?
We're doing pretty good. We got just a little bit longer. It tried cycling the valve again, and it just turned that off. Yeah, it's cycling. The high voltage interlock is going in and out. Okay, we are reading differently now. We got 4.5 microamps DC. Let's switch to PG. Let's go to PG1, see if PG1 is maybe the source of our issue. PG1 is negative 9.47, so the gauges on this one are not quite correctly calibrated. Let's go ahead and switch to voltage reading, just because we're going to load it less. It's not really how you're supposed to read these test points, but we're going to be doing it that way, because I don't know what's going on quite yet. Okay, so we got 0.191 volts. Let's go ahead and vent our load lock, see if that goes up. 0.191, that's stable. Pump it down again. Yeah, not changing. And I am on PG2, which is what I want to be on. Huh, interesting. Don't really know what that was, but we're stable now, so. Okay, we're gonna proceed. If it does reoccur, we're gonna look into it more. So we'll go ahead and leave the meter on it, just so we can. Oh, it just went up. And it's still going up.
Are you in current or voltage?
I'm reading voltage right now. So it seemed like when I touched the probe one time, it like cycled the valve. So I was like, that. I was like, that's weird. So we're at 0.156 volts. 0.157. So we are going up slightly. So that does kind. Let's check PG1. It's going to be PG1 will be more sensitive to a load lock issue. Well, it's not dropping. Let's see if we're at 151 still on, or 0151 on PG2. No, that went down actually quite a bit that went down a lot. Okay, so let's let the load lock cycle happen. So it seems like we have a leak in our load lock door. So that's fun. Yeah, never seen that before. We were load locking samples before the stream and everything. That's really funny. So there's probably contamination on the inside of the load lock door. Something on the O-ring there. So we'll cycle that a few times. Okay, let's see if that closes it up now. Okay, so we're going to vent. It's still dropping. Let's see if that continues to drop. Okay, so I think we dislodged whatever is on the load lock door, so that needs to be pulled apart and cleaned. Okay, well, it's still dropping. So it's lower than it was before even. So I'm comfortable proceeding with that. So we're saturating our filament. There we go. Cool. Let's figure out what we got. Okay, I got a lot of different flakes here, so I'm guessing that that is metal, maybe? Well, you know, let's just get the, so that's something insulating. So that, I mean, that appears pretty conductive, so that's probably metal right there. And let's run a spectrum on it. So if you want to point at this screen here, this is our Norrand software. We can zoom in on this one. We'll go ahead and do spectrum, and we'll start button. That's going to ask us some questions. We're at 15 kV. Magnification doesn't really matter. We are at 50 millimeter working distance, so we'll go ahead and close that, and that will start our acquisition. Okay, we got a peak. What do you think it's going to be, chat? Aluminum. Okay, it appears the flakes are aluminum. Yeah, we got a little bit of aluminum, magnesium, fluorine peak. I am suspect of that, but okay, that is cool. Let's go ahead and zoom out some, and we'll just we're going to crank our probe current up. So a lot of probe current. So now we're imaging. We're hitting everything on the stub with electrons. Our working distance is a little bit low. I'm going to bring that up some just so we get a little bit more pointed at the detector. Zoom out, point at our whole stub. Okay, now we're at right at 15. Okay, so let's do a. So that's our third. So this is so that's spectrum 3. So let's do spectrum 4 now. 50 million working distance, all good. Okay, so now we're getting spectrum off of like the whole stub. So this is like anything that's on this stub is going to be generating stuff. Expect to see a lot of carbon, a lot of oxygen, because that's what the carbon's made out of. So we got our big old oxygen peak there. Don't know what that peak is yet. I think that's probably an aluminum peak. No, aluminum's not showing up, or that's not aluminum. Let's see here. Okay, it's starting. Yeah, that's not. Neither of those are what's going on. Okay, it's getting a little bit confused. I don't think we have enough counts. Or it looks like the peaks we want are a little bit buried. So we can let it capture some more. Okay, now it's starting to think about aluminum. There we go. Okay, that's now on peak. That's not. I'm not liking the data from that. Let's just zoom in and check out a few more, and then I think we'll wrap it up the stream. But aluminum does point to turbopump rotor, I believe. There we go. Yeah, big old aluminum peak. We've got, that might be a gold peak. No, that's probably not a gold peak. Yeah, I'm just seeing aluminum across the board there. A little bit of copper, probably. But alumina is like a lot of peaks that stack on top of each other in kind of weird ways, so. But yeah, there's a lot of, just look at the way that this fractured, you know? That looks like something high speed happened, which would align with our turbopump theory. Map Labs, what is your professional opinion here? I'm a little bit short on time tonight, so we are going to be wrapping up here in just a little bit, but we'll go ahead and shoot one more spectrum. Another very narrow aluminum peak on that one. A lot of really small debris, a lot of fractured edges. So I think pretty sure the VAT valve is not aluminum. We can find out, but because of the magnetic shielding requirements. So I think that we got a turbo pump rotor is what we're looking at. And then also all of these round things, that's also like, that's another thing that happens when you get like a high speed like impact, is you get a lot of stuff that rubs against each other and kind of rounds out. So yeah, that's what we found. A lot of little chunks of aluminum. And I'm gonna look at this a little bit more closely when I got some more time to capture some images and do some analysis, but yeah. I think that's where we're going to wrap the stream up for the evening. Thank you everyone for joining us. Had fun installing OpenBeam interface. Had fun checking out what our chunks of metal are made out of. This gives us, I think, some good information to work off of here. And yeah, we're going to probably open Merlin up then and see where else metal's gone, so we can keep it out of the new pump and move on from there. Yeah, long thin fibers from the wipe. I agree with you on that one. So cool. Thank you everybody for joining, and we'll see you next time.